Hello, and welcome to Empowered Learning. This particular video will be about rational expressions and functions. In particular, we want to define what a rational expression is and differentiate that from what a rational equation is. And then after that, view all the different ways and techniques that we will reduce rational expressions. So let's get started. So the first thing that we need to do is identify what do we mean when we say a rational expression. Well, if we think about back when we first started to define what a rational number is, we know that a rational number is just something that can be written as a fraction. So like 1/3 or 2.56 with a line over it meaning a repeating decimal. Or if we have something like 1/4, which is equal to 0.25, which is a terminating decimal. So anything that can be written as a fraction. Now, in general, a rational expression is just what I like to call a polynomial fraction. Okay? And I call it a polynomial fraction because the way that it is defined is a rational expression is the quotient. We'll just go ahead and write this in now. A rational expression is a quotient or ratio of two polynomials, meaning polynomial in the numerator, polynomial in the denominator, with the denominator not being allowed to equal 0. Okay. Now, a rational equation, which you'll see in the video that follows this, is two rational expressions that are equal to one another. Okay, or at least you're stating that they're equal to one another. We'll see in some cases that just because you put two rational expressions equal to one another, that does not necessarily mean that there is a solution to that particular equation. Okay? And we'll also see that although we may get solutions from the process of solving a rational equation, not all of the solutions will work. Okay? So let's go ahead and move on. So some examples, other examples of what rational expressions would look like are 4/5, 3x minus 10. And so we know that this in general is a linear type of expression, but in the grand scheme of things, we know that any linear expression is under the umbrella of a polynomial. And so this is a polynomial of degree 1. And anything that we take and divide it by 1 can now be considered a rational expression. Okay? We also have these expressions here as well. So all these are considered to be rational expressions because you have a polynomial in the numerator, polynomial in the denominator. And of course, it's valid for all values of the variable where it doesn't make the denominator equal to 0. Okay? All right, so moving on. So when a rational expression is used as a function, we must pay attention to what real number values we plug into it. Okay? The set of real numbers that do not make the denominator of the resulting rational expression equal to 0 is what is called the domain of this rational expression or function. Okay? And so the domain is important because domain is actually how we define what values, we'll say, of x that we can plug into a function, whether it is a rational function or quadratic function, square root function, nth root function, so on and so forth. Okay. When you think of domain, you can just think of it as sort of like your email account that you may have, right? So, of course, most emails have whatever the address is, and then part of the address is the domain name. So whether that is a Hotmail, Google, Yahoo, Live, whatever it may be, your work email, or what have you. Okay. In order to get into that account, you must have the correct credentials, meaning you must have the correct name and the password. And so, in a sense, your email account is like a function that has two variables in it, and you have to plug in the right things, or the legal things, I should say, into both variables simultaneously for you to be able to access that account. Okay? If you don't, then it rejects you. And so similarly with in mathematics, it's the same way. If we do not plug in legal x values into expressions of functions, then the result that we get will be something that is illegal. And in this case, what is illegal is anything that you plug in an expression that yields out something that is not a real number. Okay. All right. So moving on here, we want to talk about the domain of the function. Let's consider the function f of x, the function g of x, and the function h of x. And what we want to do is find the domain of each of these functions. And so when we talk about domain, there's two things in particular that we are looking for. We want to make sure that, and this is the way that I write it, we don't plug in any value for x that makes us divide by 0, and we don't want to plug in any value for x that will end up making us have a negative number under an even nth root sign. Okay. Now what we're going to concentrate on today is mostly this one, making sure that we do not plug in an x value that will make us divide by 0. Okay. So for this first one here, we see that since we have a variable in the denominator, there's potential for us to be able to have plug in an x value that will make us divide by 0. Of course, if we see here, if we plug in 3 in for x, then we know that 3 minus 3 is equal to 0, and that's the one thing that we can't have. So we know we can't have the denominator equal 0, so we say x minus 3 can't equal 0, which in turn means that x can't equal 3. So our domain will consist of all real numbers except for 3. And this is how we write it in interval notation. Okay? Similarly, for g of x, we see that we have the product of x and x plus 5. So here we need to take that product and say that it can't equal to 0, which means that either x can equal 0 or x plus 5 can equal 0. And hence we see that we can't plug in the values of 0 or negative 5. Okay? And again, this is how we write it in set notation. This is how we write it in interval notation. Okay? And so again, what this means is as long as we plug in values that are not 0 and negative 5 in this case, then we will plug in the next value that is a real number that will yield us or spit out a real number as a result. Okay? All right, so let's go ahead and move on. So for h of x, let's go back and look at that right quick. The function h of x, we notice that we just have 21 in the denominator. So there is no variable x in the denominator. And for this reason, this particular function could actually be looked at this way. Okay? If you notice, this is in the profile of a linear function with a positive slope and a negative y-intercept. Okay, and of course we know that that this could be reduced to 1/7, but here in general we know that any x value that we plug in that is a real number, we're going to get out a real number as a result. And so because of that, we know that the domain of h of x is just going to be all real numbers. Okay. All right, so we've talked about the basics on what a rational expression is, and we've talked about the domain of a rational expression or function. So now we're going to get into some other basic properties before we get into a lot of the examples that we have. All right, so basic principles and properties. So if we have a rational number or a rational expression, let's say a divided by b, then we know if we were to multiply the rational expression by 1, but made 1 look like something divided by that same something, in this case I'm saying c divided by c here, then we know that that would be equivalent. And so this is the same sort of thing that we do whenever we make equivalent fractions. Okay, so for instance, if I had 1/3 here, I know that if I wanted to make an equivalent fraction with the domain of 12, I know that I would multiply this fraction by 4 over 4, which is another way of saying 1, and thus I would have 4/12. Okay, we're going to do that, but do it on a higher level where we're talking about expressions that have letters and numbers here. The point that I want to make is that a lot of people make this mistake when they're first learning how to deal with rational expressions. And so the mistake is to think that when you have a property like this, that since you see those C's in the second term of both the numerator and denominator, that you can just quote unquote cancel them out. Okay. First thing only thing that we cancel is stuff that goes to 0. Okay. This action that people attempt to do is called reducing to 1. And the issue with trying to reduce to 1 this way is that our original rule said this. In other words, it said multiplication. Notice that you have addition here. Whenever you have addition or subtraction that is separating the terms that you're wanting to look at, you cannot break them up. Okay. Now, if you have multiplication, like in this case here, then you could come and reduce to 1. But not like this. Not like this over here. Okay. And so to prove my point, I've taken an expression, 3 plus 4 divided by 4 plus 4. And again, if we were quote unquote reducing to 1, we should get the same outcomes here and here. But notice that we don't have that. Okay. So here, 7/8, whenever we do it the way that we're supposed to via order of operation, is not the same thing as 3 over 4 here whenever we illegally come in and try to reduce these 4s here to 1. Okay. So just want you to be mindful of that as we go through the examples here, that anytime we have a term that's attached via addition, we cannot reduce those terms to 1. Okay. All right. So when we multiply rational numbers or expressions, we know that we just multiply numerator with numerator and denominator with denominator. Okay. And when we do division of rational expressions, what we need to do is what's called keep, change, flip. Okay. Or KCF. Okay. So we keep the first fraction the same. We change the operation from division to multiplication, and then we flip the other fraction, meaning we take the reciprocal of it. Okay. And then we just multiply those together. Okay. So and a quick example, let's say we have 1/3 divided by 4/5. Okay. So we keep the first fraction the same, which is 1/3. We change from division to multiplication, and then we take the reciprocal of, or flip, the bottom fraction. Okay. And so then from this point, of course, we look to see if anything in the numerator will reduce to 1 with anything in the denominator, and we see that in this case it doesn't, so we just multiply numerator with numerator and denominator with denominator. Okay. All right. So in another example, and I'm going to go ahead and come up with one here right quick, we can have a situation where we need to reduce some before we actually do the multiplication here. So I'm going to change this slightly. And so I'm going to change this from a 5. Well, let's see. I'm going to do this as 4 over 9 now, and erase all this other stuff so you can see how that would work. Okay. All right, so in this example, we'll do everything the same, which is we'll keep first fraction the same, change the operation of multiplication, and now we will flip or take the reciprocal of the bottom fraction. And so now you see here the 3 and the 9 both have a common factor of 3. So we say 3 goes into 3 once, and 3 goes into 9 3 times. And now we just multiply numerator with numerator and denominator with denominator. Okay? So that's how division of rational expressions would work. And so again, here we have the whole thing of the keep, change, flip. So just in case you forget that, you can always come back and look at this video. All right, so whenever we add or subtract rational numbers or expressions, it's pretty much the same. We have to have a common denominator, whether that common denominator is a number or an expression. It has to be the same. Okay? If we do not have a common denominator, we have to find one first before we do the addition or subtraction of rational numbers. And so we'll get plenty of practice with that as well. And please remember that whatever you do, the denominator, the common denominator, cannot be equal to 0. Okay. All right, so now let's get into some examples here. So for this first one, we notice that here that we're just going to reduce the fraction 6 over 57. And if you notice here, the digits on bottom, 5 and 7, they add up to be 12. So by our divisibility rules, we know that we know that 57 is divisible by 3. Okay. So what we're going to do is take a factor of 3 out. So I'm just going to rewrite this as 2 times 3. And of course, I think this will be 3 times 19 if I'm correct. Okay. And so now we see that we have a common factor of 3. So that reduces to 1. And notice how we have multiplication here. And hence that's why I'm able to reduce. And so now from here I just have 2 times 1 is 2. 1 times 19 is 19. And that's what the reduced fraction is. Okay. In the second example, we see that we just factor out a 2 as greatest common factor out of the numerator. And then from there we see that both 2 and 4 have a common factor of 2. So 2/4 reduces to 1/2. And then after that we just multiply everything together. So in example C, we'll factor out a common factor of 3 in the numerator. And then we see from here that 3 goes in 3 one time, or we're reducing to 1, and then we just write what's left, which is a plus 1 divided by 1. And of course, anything divided by 1 is itself. All right, so in the next example, you'll see that what we're doing here is we factor out the common factor of 2 in the denominator. And then from there, you can see we have a minus b in the numerator, but we have b minus a in the denominator. And so if you notice, they're very similar to one another. Okay. And the difference in between a minus b and b minus a is just b minus a is the same thing as -1 being multiplied by a minus b. And if we go ahead and distribute our -1 here, we'll see that. So this gives us a negative a, and a negative times a negative is a positive. And so from that, if we use commutative property of addition, and switch around, then we have b minus a. Okay? And so from there, if you notice, I factor out a -1 coming from here to here, which leaves me with the negative b plus a. And of course, if I use a commutative property, I will switch this around and thus make it a minus b. Okay? And so just like how I said b minus a is the same thing as a negative a minus b, similarly, we know that this is the same thing as a negative b minus a. Okay? So my whole point is that these two expressions here are just opposites of each other. Okay, and so we've rewritten this particular expression here in the denominator to basically match up and saying the negative of a minus b. Okay, and so now from there we reduce the a minus b. Notice how we're reducing everything, not just the a, not just the b. We're reducing the whole expression a minus b to 1, because we see it both as a factor in the numerator and the denominator. And so the reason why we're saying that is because this is understood to be this times 1, and we have a negative 2 times a minus b. So we have multiplication going on. Okay, and so from there we reduce the a minus b's, and then we end up with negative 1/2 as our answer. Okay, so for our next example, we'll factor out the greatest common factor, which is 7. And if you notice here, we have 7s that are common factors in numerator and denominator. So we will reduce those to 1, and we just have x minus 2 over x as our answer. Please note that this is the final answer, meaning that this is this particular rational expression in its reduced form, or lowest terms. Okay, you cannot come here and say let's go ahead and reduce the x's to 1 here. You can't do that, because remember, you have subtraction here. Okay, if you had x times 2 divided by x, then you could actually go in and actually reduce the x's. But since you have subtraction here, you can't do that. All right, so moving on to the next set of examples here, we see that for example F, we have a cubed minus b cubed divided by a minus b. And so a cubed minus b cubed is what we call the difference of 2 cubes. And so with the difference of 2 cubes, you'll see that I've factored this out to a minus b times the expression a squared plus ab plus b squared. And so that's just a common special factoring type case there for the difference of 2 cubes. And so in the denominator we have a minus b, and thus by factoring out the difference of 2 cubes, we see that we have a common factor of a minus b both in numerator and denominator. So we reduce those to 1, and we see that all we have left is our expression a squared plus ab plus b squared. Okay. All right, so for our next example, what we'll need to do is factor out both the numerator and the denominator. Okay, and so I'm going to start off here by just pulling out the greatest common factor in between all the terms in the numerator here. So I'm going to erase this because I made this a little long. So here we see that all the coefficients are even, so we can at least factor out a 2. So that'll give us 2x squared minus 5x, and that should be a minus 3. Okay. All right, in the denominator, we'll see if we can go ahead and factor this out. And so doing this by trial and error, this will be 2x and x. Since both of our signs are plus, we have plus. And the factors of 5 are just 5 and 1, so we'll put a 1 here and a 5 there. And so if we multiply the outer and the inner terms, we see that 2x times 5 is 10x, 1 times x is x, so 10x plus x is 11x. So we're good here. Okay. From here we need to factor out the numerator now. So go ahead and finish up writing this. And so here again, doing trial and error, we'll have 2x and x. Since the sign is minus, minus, one of these is going to be plus, one of these is going to be minus. I'm going to put the minus here and the plus here. And so the factors of 3 are just 3 and 1. So I'm going to put the 3 here since I need the middle term to be negative. The bigger factor needs to go by the negative sign, and we'll put the 1 here. Okay. And of course, if we multiply the inner and outer terms, we'll see that they end up being negative 5x, so this works as well. All right, so now that we're here, we see that we have a common factor of 2x plus 1. So 2x plus 1, those things will reduce to 1. And what we have left is just 2 times x minus 3 divided by x plus 5. And so that will be our final answer there. Moving on to the next example, you'll see that we have 2ab plus 2by plus 3a plus 3y, all that divided by 2b squared minus 7b minus 15. Okay. Now, notice that we have 4 terms here instead of 3. Okay. So we're not dealing with trinomials here. We're dealing with a polynomial with 4 terms. Normally, in this case, we try to do what's called factor by grouping, which is what is done from here to here. Okay. Notice how I group the first 2 terms together, the second 2 terms together. And so in each group, I'm trying to factor out the greatest common factor. And I find that for the first 2 terms, the greatest common factor is 2b. The second 2 terms, the greatest common factor is 3. And it works out nicely here because we see that inside the parenthesis, we have the same thing. So hence, what we're able to do is factor out what's in the parenthesis there, which is a plus y, out of both terms, and then just write what's left. And so that we see we have 2b is left in the first term, and plus 3 is left in the second term. In the denominator, if we factor out 2b squared minus 7b minus 15, we get 2b plus 3 times b minus 5. And then from there, we see that we have common factors of 2b plus 3, both in numerator and denominator. So we reduce those to 1, and then we just write what's left. Okay. All right. So we'll go ahead and move on here. So the next thing that we want to do for each rational expression is to find an equivalent rational expression that has an indicated denominator. Okay. So in other words, we're making equivalent polynomial fractions. Okay. And so in this first example here, we know that we have 3, which is the same as 3 divided by 1. And so we need to find a common denominator. Well, not really a common denominator, but yeah, we need to find a common denominator between 1 and a plus 1, which is just a plus 1 in this case. So essentially all we're doing is multiplying our fraction 3 over 1 by a plus 1 over a plus 1. Okay? And then hence we get our equivalent polynomial fraction, or said more proper, our equivalent rational expression. Okay? Now, in example B, we notice here that we have x over x minus 5, and we want to figure out what is the equivalent rational expression with the denominator x squared minus x minus 20. Okay, so the first thing that we need to do is factor x squared minus x minus 20 to see what it is composed of. Okay, so if we look here, this will be x and x. Since we have minus minus, that means one has to be a plus, one has to be a minus. And we know the factors of 20 that have a difference of 1 is 4 and 5. So we'll put 5 here, 4 there. Okay. So as you see, we have a factor of x minus 5 within this. So the LCD that we need is just going to be x plus 4, x minus 5. And so the one thing that we need to multiply our expression x over x minus 5 by is x plus 4. Okay, so if we do that, we know in the denominator it's going to come out to be x squared minus x minus 20, but in the numerator we're going to have x times x plus 4, which we could either leave it like that, or we could go ahead and distribute the x into both terms and just write it as x squared plus 4x, and all that over x squared minus x minus 20. Okay. All right. So for the next example, sort of the same thing. We see here that we have a fraction, or rational expression rather, a divided by 2a plus 1, and we're trying to find an equivalent fraction with 4a squared minus 16a minus 9. And so from there, we see that if we factor out 4a squared minus 16a minus 9, we get 2a plus 1 times 2a minus 9. Okay, so we see that the 2a plus 1 is the same. The thing that it's missing is 2a minus 9. So we multiply both numerator and denominator by 2a minus 9, and we see that once we do that, this is the answer that we get. Okay, for the next example, notice here we have a situation where the denominators that we have look very similar. Okay, and remember earlier when we were saying that a minus b and b minus a are only different by each other because one was the opposite of another. Okay, meaning that b minus a was the same thing as negative a minus b. Well, we have the same sort of thing going on here. So we see that in this case we have x minus 1 and 1 minus x. So the difference in between x minus 1 and 1 minus x is just a negative. Okay, so here this means that this is the same as negative x minus 1. Okay, so we see the only thing that here that is missing is the negative, or the understood negative 1. So whenever we whenever we want to rewrite what this is going to be in order to get a denominator with 1 minus x here, we just know we need to multiply numerator and denominator by negative 1. And thus we just have negative 7 divided by 1 minus x. Okay. All right, moving on. So now what we're going to do is multiply rational expressions. And so when we do this, we want to try to the best of our ability to reduce as much as we can first before we start actually multiplying. Okay. So in this first example here, I'm just going to put everything together to be clear. So I'm going to have 3 times 2 times a. And then here for 4a, just going to say 4 times a times 9. Okay. And so I'm going to rearrange this to where everything kind of lines up. Don't have to do this, and I won't be doing this in future examples, but I'm just doing it in this one to be clear on why everything reduces the way that it does. Okay, so if I rearrange this, I can have 3 times 2 times a again, but in the denominator now I'm going to write 9 times 4 times a. And of course, if I break everything up now, I could write it like this. And if you notice here, we have these a's reduced to 1. We know that 2 over 4, that reduces to 1 over 2 because 2 and 4 both have a common factor of 2. And then 3 and 9 both have a common factor of 3. So this will reduce to 1/3. And so now from here, we just now we do the multiplication in the numerator, do the multiplication in the denominator, and we see that our result is 1/6. Okay. Now, what we could have done to shorten this process here is to say 3 goes into 3 once, 3 goes into 9 3 times. These a's reduce to 1. 2 goes into 2 once, 2 goes into 4 2 times, and then just go from there straight to here. Okay. But I wanted to make sure, at least in this example, I wanted to show why we could actually do this shortcut step here. If you can actually see everything, it's because of, if we wrote this out the long way, it still ends up being the same thing. Okay. All right. So on the next example, we see we have 3x divided by 5y times 14y squared divided by 9x. And so if you've seen here, I've already written this one out. I have rearranged everything to where everything that has x goes together, everything that has y goes together. And then I've factored out 9x into its prime factorization here. And so you see that we have those 3's in common and we have those x's in common. So we reduce those to 1. I've done the same thing with the second example here. And we see that we have in common 7's that reduce to 1, have in common y's that reduce to 1. Oops, circled the wrong thing there. But I think you get my point. It's one of the y's that reduces to 1 there. So I meant to circle these two. Okay. And so now everything else that's circled is what is left. Okay. Circled in black, that is. So we see that that's our answer. All right. So for this next one here, first thing that I'm going to do is I notice that 6 and 2 have a common factor of 2. So 2 goes into 2 once, 2 goes into 6 3 times. Okay. The other thing that I'm going to notice here is that right here in the numerator, I have a common factor of -2. So if I do that, and I factor it out, I'm going to have -2 times x plus 2, and that's going to be over 1 now, times 3 over, and now in the denominator for the second fraction, we have a common factor of 3. Okay. And so now we see we have a common factor of 2 in the numerator and denominator. So that reduces to 1. And now we just multiply what's left. So we have -2 times 1 times 3 is a -6. 1 times 1 is 1. And so, of course, anything divided by 1 is itself. Moving on to the next examples. We see that we have a squared minus 4 times 7 divided by 2 minus a. And so here we notice that a squared minus 4 is actually the difference of 2 squares. Okay, and we know that the difference of 2 squares, when we deal with that, just factors out the a minus b times a plus b. Okay, where in this case, our b is 2. So this is why you see going from here to here, we have a minus 2 times a plus 2. Okay. And notice, since we have an a minus 2 here, we want to change the way that 2 minus a looks to now a negative 2 plus a, or a negative a minus 2. Okay. So once we do that, we have common factors of 2, and we just multiply what's left. And we see that we end up getting a -7a minus 14. So looking at that similarly, in example E here, we're going to factor out the greatest common factor in the numerator of the first fraction, which is a 3. Here we know that 6 is 3 times 2, have x, and then the greatest common factor in between the denominator of the second fraction is just x, so that'll be x minus 1. Okay, so we have common factor of 3 that reduces to 1, common factor of x that reduces to 1. And we have a common factor of x minus 1 that reduces to 1. And so the only thing that we have left here is this 2 and all these 1s. So in the numerator, we multiply, we just get 1. In the denominator, we multiply 2 times all the 1s, and we just get 2. All right, so our next example here, we see that we have 10x plus 5 divided by 5x squared plus 5, and all that is times 2x squared plus x minus 1 divided by 4x squared minus 1. And so if you see from the first rational expression here, we factor out the greatest common factor of 5 in both in the numerator and the denominator. In the second fraction, we factor out this trinomial, and it ends up being 2x minus 1 times 2x plus 1. And then in the denominator here, we recognize that that is another difference of 2 squares. Okay, and so if we actually wrote it out, it would look like this. Okay, where 2x quantity squared is just 2 squared, which is 4 times x squared, and that total would be 4x squared. Okay, so again, we know that anytime we have the difference of 2 squares, we know there's got to be a minus b times a plus b, where in this case our a is 2x and our b is 1. So that's how it comes out to be that way. And so now from there we reduce all the common factors to 1. We have a common factor of 2x minus 1 and a common factor of 2x plus 1. And then after that, oh, and we also have a common factor of 5. Forgot about that. And so then from there, we just write what's left, and that's what we get. Okay, so from this point, we've reduced some basic rational expressions. We've been multiplying some. Now we're going to go into dividing some rational expressions. Okay, and so same sort of thing. The only difference now is that we want to remember that whenever we're dealing with these rational expressions, that we want to keep, change, flip. Okay, so for the first expression here, we are going to say 15 divided by 17 times 17 divided by 10. So of course we have a common factor of 17, so that reduces to 1. And now we have 15 over 10, and 15 is just 5 times 3. 10 is 5 times 2. Have common factors there, and we see that our answer is just 3 over 2. Similarly, for example B, we see that we keep the first fraction the same, change to multiplication, and then flip or take the reciprocal of the bottom fraction. And then from there, as you can see here, I've rearranged this so that I can have the 8 over here and the 3 over there, so that we can clearly see that 8 divided by 4 is just 2. Or that, put another way, 4 and 8 have a common factor of 4, and it reduces to 2 over 1. And then from there, we just multiply what's left. Okay. In the next example, we have 36x divided by 5y times, and now we're going to take the reciprocal of, or flip, the second fraction. So I have 35y divided by 20x. Okay. And so from here, we know that 5 and 35, common factor of 5. So 5 goes into 5 once, 5 goes into 35 7 times. Y has a common factor of both y's are common factors, so they reduce to 1. Let's see if I can get that. We have x's here. Both of them reduce to 1. So now I'm going to rewrite everything here. So we have 36 times 7 in the numerator, and we just have 20 in the denominator. Now, 36 is 9 times 4, and 20 is 4 times 5. So both 36 and 20 have a common factor of 4. So 4 goes into 36 9 times, 4 goes into 25 times. And so now once we're done here, 9 times 7 is 63, and 5 is by itself. So 63 over 5 is the final answer there. All right, moving on to the next examples. So we see that for example D, we have this particular rational expression here. And so we go ahead and factor out a 2 in the numerator of the first rational expression in the numerator and factor out an x in the denominator. And hence we have 2 times 2x minus 1 divided by x times x minus 5. Okay, and then for the second rational expression, we factor out the numerator, factor out the denominator. Okay, and then from that point, we do keep, change, flip. So we keep this the same. Oops, let's go back here. Sorry about that. So we keep this fraction the same. We change the operation from division to multiplication, and then we flip or take the reciprocal of the bottom fraction. So we're going to flip this. And so once we do that, we see we get what we have here, and then we just reduce all that we can. And so what I did is going from this step to this step, I've rewritten everything in order so that you can see how it all lines up, and then reduced accordingly. And of course from that, the only two things I had left was 2 in the numerator, x in the denominator. So that's what everything reduced to. All right, in the next example, we're going to do the same thing. Since we have division here, complex rational expression, we will say 3x squared plus 3 divided by 5 times 5 divided by 3x plus 3. Okay, and so now with our first rational expression, I will factor out the greatest common factor, which is 3. And then do the same thing in the denominator of the second fraction. And so now we see that we have 5s that reduce to 1, 3s that reduce to 1, and all we have left is x squared plus 1 over x plus 1. Okay, and so notice here, whenever we have x squared plus 1, that we cannot reduce this at all. So cannot reduce this at all. Okay, so remember, we just have addition here, so we can't really do anything with that. And if we try to factor out x squared plus 1, that's going to be a prime factor, so we can't really do anything with that. Okay, so we have to kind of leave the answer as is. Okay, all right, so let's go ahead and move on to the next example here. So for this last one on this particular page, we see that we have x squared plus 5x plus 6 divided by x plus 2 divided by x plus 3, all that together. And so we start off by factoring the numerator first, and then from there, whenever we convert that, we know that everything that's in the numerator here will be just whatever that is over 1. Okay, so that's why when we look at this, all this could be looked as that divided by 1. So we do keep, which is x plus 2 times x plus 3, all that over 1. Change, division and multiplication, and then flip. And so that's why we have x plus 3 divided by x plus 2. In fact, reduce the common factors of x plus 2 to 1, and then we just write what is left. Okay, and for there we have 2 factors of x plus 3 in the numerator. So we know that that'll be x plus 3 quantity squared, or we could FOIL that out, and it'll be x squared plus 6x plus 9. Okay? Either answer is acceptable. All right, so from this point here, we'll keep on. So in this case, we have 6x divided by a, all that divided by x. And so first thing that we want to note is that x here is the same as x divided by 1. So we could sort of look at it this way. And then from there, we have 6x divided by a times 1 over x. We see that we have a common factor of x. That reduces to 1. And so when we multiply what's left, we just have 6 in the numerator, a in the denominator. Okay. In the next example, we need to apply our exponential rules first before we actually start trying to do the complex division here. So for our first term, for our first rational expression in the numerator, we know that RT quantity cubed is just R cubed T cubed, okay? And all that's over RT to the 4th, okay? Divide. RT squared quantity cubed is R squared T raised to the 6th. And all that R squared over T cubed, okay? So from this point, if you notice, we have a common factor of R squared in numerator and denominator. We have T6 divided by T3. We know that that will end up reducing to T cubed. Over here, we have T cubed divided by T to the 4th, and that will reduce to just T. And R cubed divided by R will just reduce to R squared. Okay? So when we do all that, what we end up with here is R squared divided by T divided by, and now we have T cubed divided by 1. And so from here, we could go ahead and do our keep change flip. Okay, so I'm going to come over here and do that now. So that'll be R squared divided by T times 1 over T cubed. And once that's done, then we just have R squared in the numerator. T, or T raised to the 1 times T raised to the 3 is T raised to the 4. So this would be our final answer here, after we come here and do this. All right, moving on to the next example here. We see that we have another case of dealing with exponentials. So we go right out the box here and start to do the keep change flip. So we keep the first fraction the same, change the operation from division to multiplication, and then take the reciprocal of or flip the bottom fraction. Okay. So from this point, if you notice, I rearranged everything from this step to this step to have everything that has a base of x with its exponential expression together, and everything that has a base of y. The reason that I want to do that is because if I do that, then I know that I can apply my exponential rules. Okay, so if you notice here, we're going to be heavily using this particular exponential rule. In other words, subtracting exponents whenever we have the quotient of rational expressions. Okay. So for this first one here, we take 3a plus 1 and subtract that by 2a minus 1. And for our exponential expressions that have y's, we'll have 3b plus 4 minus 2b minus 3. Of course, we distribute the negative across this exponent here, do the same thing here and here, and then we simplify. And when we simplify, we end up getting x raised to the a plus 2 times y raised to the b plus 7. Okay, and so that pretty much wraps up what we need to do here. So in the second portion of this particular video, or the second part, we'll do adding and subtracting of rational expressions.